Hello everyone, let's find out the electric field at a point on the equatorial plane of a dipole. Now if you have a charge at some point here, if we call this as charge say minus q, and then a charge somewhere here, if we call as charge plus q, let this point be point A and this is point B, then we saw that a plane which is passing normally to this axis and passing through center of the dipole, this plane is called as an equatorial plane. But then from side view what we see would be just a line, hence we just draw a line here, but it's actually equatorial plane. So let this be the point, we'll call as point C, where we need to find the electric field. We'll mark a center of this, we'll call this as point P. So point P is a point on the axis which is at the center of the two charges. The distance between the two charges is given as 2a. That would mean that distance between A to P would be A and distance between B to P would be A. Let the distance from the point P where we need to find dipole, let this distance be small r. So we need to find electric field at this point C at a distance of small r from the center of the dipole. Again here the charges at point B and A, that is the charges plus q and minus q, will create their own fields and we need to add them vectorially. So let's first find out what is the field which the charge plus q creates. Now the electric field from the charge plus q will go out radially like this. So the field goes out at this point, the field goes out like this. Let us call this as E suffix plus as a vector quantity. So this E is given as kq by r square, is what is the form of E. But here in this case, if you write as E positive, it is just indicating that this is the field which the plus q creates. It will be k into q, distance would be bc the whole square. In terms of vector form, E is equal to kq by bc would be, now this is a right angle, so bc would be the hypotenuse. From Pythagoras theorem, bc square would be equal to a square plus r square and vector quantity will have direction, so it is along BC, is what is E plus. Similarly, even the charge minus q will create a field and that field would be towards the charge only, because for a negative charge the electric field is towards the charge. We'll call this as E minus. So E minus is the field which the charge minus q creates. So E minus in magnitude would be kq by, to remember that in case of electric field we just put the charge magnitude not with polarity, because the direction takes care of polarity. Kq by Ca the whole square, that is equal to E minus is equal to kq by Ca would be, it's again the hypotenuse square, that would be equal to a square plus r square. Now this would be along Ca. The net field, the total field, if we call that as E suffix E, just to indicate that this is the electric field for a point on the equatorial plane. This is equal to E plus E minus. This is called as principle of superposition of fields. Keep in mind that this is a notation, it's a single term, and this is one more term. If somebody can't remember this, then you can write it as EA and then EB. It's up to you all, but the idea is the same. Now here, the vectors are different directions, and then the angle is not known to us between these two quantities. So what you can do here is, to make it more simple to be solved, we will use vector resolution. That is, we will find the components of vector and then add them by component form. To do that, at the point C, we'll put two axes. An axis like this, an axis like this. An axis, this goes like this. So we'll call this as x-axis, this would be y-axis, and recall that this would be the field because of the positive charge. Now, if suppose the angle made here is theta, if this is theta, then we can prove that x-axis and AB would be parallel lines, and this is the transversal, so the angle made here also is theta. If it's confusing, then think of like this. Imagine that if the point C was at point P, just imagine that if point C, just redraw this. This was point A, B. I'll just draw some other scale here. So this is point, say, A, this is point B, this is point C. Suppose imagine that the point C was at point P. And what will happen is, the field which this charge at point B, which is plus Q, now the field this creates would be going like this. Suppose imagine that the point C is somewhere here, then the field from here will go like this, So the angle what it makes with x would be some angle here. That is, in the initial case, this is minus x direction. So the angle between the field which charge B creates, that is E plus and x are in same direction. If the point is somewhere here, then minus x is like this only, but the field which the charge at B creates would be going like this. So the small angle created, this is the angle created. If the point is somewhere here, it's point somewhere here, then minus x is always same, it's always parallel to AB, but the field now will be aligned like this. So the angle what the field makes with x would be now different. So what is seen is, each time the angle what is made here is same as this angle here. This and this would be same. So in simple term, you can say that the angle made between BC and AB is same as the angle which E plus creates with the minus x-axis. This is what the angle is. You can prove it in many ways. This is one way to prove it. You can again use geometry property and then you can prove it also. But the idea is, the angle here is positive. That would mean that if we redraw that, this is what is E plus, we have two axes here. This is plus x axis or plus y axis, and this is minus x axis. This is E plus. Since this angle is theta, this component would be E plus cos theta, and this would be E minus of sin theta. Again, keep in mind that E minus is a single term. It is not E minus sin theta. It is E suffix minus, which is a single term into sin theta. Similarly, if the angle is theta here, this will be theta by same logic. That is because x-axis is parallel to AB and then CA is a transversal. So even in this case also, this is a field. We take the two axes like this. This is E minus angle is theta here. This was minus x-axis. That will be E minus of cos theta, and this would be E minus of sine theta. If you add the four components, now we divide the two vectors into four components now. That is E plus and E minus has been divided into four components. Out of four components, observe carefully that E minus, because it's E plus here, Z plus, okay, that is E plus sine theta and this E minus sine theta, these two are in opposite direction, and also E plus and E minus is same in magnitude as given here, which means the y components of both the fields gets cancelled. Now what remains would be this plus this, and these two act in same direction. Hence, the net field would be, this equation now becomes E along the or any point on the equatorial plane is equal to, it will be just adding up the cos components. So it will be E plus of cos theta plus E minus of cos theta. But then E plus and E minus is same in magnitude. So it becomes KQ by A square plus R square, twice of it, into cos theta. And let's find what is cos theta from this triangle. From this triangle, cos theta is equal to, it will be adjacent. If you look at triangle APC or triangle CPB, cos theta would be adjacent, which is A by CA, which is the hypotenuse. So cos theta is equal to A by, this would be under root of A square plus R square. It's a hypotenuse. Therefore, putting it back here, what we get would be, it is 2k q by A square plus R square into cos theta is given as A into A square plus R square power half. Therefore, what is E along the equatorial point is equal to K into Q into 2A by A square plus R square power 3 by 2. Now recall, this term here was called as dipole moment. Therefore, E along the or any point on the equatorial plane is equal to K P by A square plus R square over 3 by 2. So this is the required expression for electric field. But here, if we assume for a short dipole, a short dipole would mean that the distance between two dipoles would be small compared with the point where we are supposed to find the electric field. Mathematically, it means that A is less than R. That would imply that A square is still very much less than R square. Therefore, A square plus R square is almost same as R square only. That is, if you're adding a very small number to a big number, the effect is almost same only. Imagine we have something like 10,000, we're adding like 0.01. So you can assume that this is like A square, this is what R square is. So in this case, take 10 power 6 here. In this case, what happens is, the value what you're getting here would be almost same as this value only. So the effect of A square is negligible to adding it to R square. So finally what we get would be E would be K P by, this becomes R square, the whole power 3 by 2, So I'll write it r square power 3 by 2, and from this 2 gets cancelled. Finally, the electric field would be equal to k p by r cube. In terms of vector form, this field is from plus to minus, but we studied in the theory class that dipole moment direction is from minus to plus. So in terms of dipole moment, we can say electric field on any point on the equatorial plane is equal to minus k p by r cube into p cap. This is the required field. To summarize the previous derivations, E along the axial point is equal to 2 k p by r cube, and E along the equatorial point is equal to k p by r cube. This is only in terms of magnitude and for a short dipole. Comparing these two, we can say that the electric field at any point on the axis is equal to 2 times the field on the equatorial plane.